Welcome to the course Scenario Development and Analysis. My name is Bruno Mazzorana. I'm working at the Institute of Environmental and Evolutive Sciences at the Universidad Austral de Chile in South America. Previously, I've been working for almost 13 years at the Department of Hydraulic Engineering of the Autonomous Province of Bolzano in the field of flood risk assessment. It's a pleasure for me to invite you to this course because I think that scenario development and analysis is a key feature of a sound hazard and risk assessment. So let's start by understanding a bit better what is the utility related to scenario development and analysis. First of all, if we think of the field of hazard and risk assessment, the utility is related to a better way to structure knowledge about uncertain processes related to hazard processes, but also related to settlement, expansion processes, and therefore related to exposure, but also related to vulnerability, and if we take all together, related also to the processes that lead to expected consequences in terms of damages, losses, and hence in terms of risk. The utilities are not restricted to natural hazard and risk assessment. In general, the utility of developing consistent scenarios are also related to the planning process in general, and more in particular to the envisioning process that is somehow defining the desired future state of a certain system. And in this case, scenarios are helpful to identify certain features of this desirable and sustainable future state that should be a help to channel the planning and the decision-making processes. Third, scenarios are useful also to, let's say, anticipate, if possible, potential consequences of certain outcomes of certain decisions in order to take better decisions at the current date about what might happen in the future. Therefore, again, scenarios can be useful for decision makers and for policymakers. Last but not least, scenarios are very useful to document possible implementation pathways. That means that if we need to implement, for example, a certain protection strategy, we might elaborate scenarios that somehow highlight at an early planning stage how this protection system is working under particular conditions. So practically, we are again anticipating the performance of a certain protection system against natural hazards, for example, by defining and describing scenarios. Yes, here I'd like to show you a bit in a pictorial way, more or less, what is the meaning of scenarios if we take into consideration the time axis. So here you can see a time axis from the point in time t0 through the points in time t1 and t2 to the future. So we can imagine that describing certain trend scenarios means to describe the so-called scenario trumpet. Here we have a region that is somehow included within optimistic scenarios, xi1, for example, the upper one, and more pessimistic scenarios, xi2, the lower one. And within these boundaries, within these possible trajectories, other scenarios can be thought of, can be defined, and these scenarios can describe particular circumstances or particular deviations of the trend due to disturbance events, due to certain interventions based on decisions. And so we can somehow unfold what is possible in a, let's say, in a structured way, and identify which are the consequences of certain disturbance events, of certain interventions along the time axis. So the scenario trumpet is a way to represent the concept of trend scenarios. But let's come back a bit to the problem of addressing uncertainties related to projections into the future. So the analysis of uncertainties, for example, associated to natural hazard events, is very important because, as you know, in devising optimal strategies against natural hazards, it's always a good thing to incorporate in your line of thought, in your string of argumentation, also, for example, worst case events or unfoldings of natural hazard processes that might occur depending on certain disturbance events and certain interventions and so on. If we focus, for example, on flood risk assessment in mountain areas, there are several sources of uncertainties. Let's list the most important ones. First, uncertainties about the range of the rheological behavior of such flow processes and about the solid liquid mixture concentrations of debris flows. So in principle, in this case, you always have to define a certain number of scenarios that takes into account the possible variability of rheological behavior depending on the solid liquid mixture concentration, and this parameter that normally is fixed in advance before you perform a simulation has a strong influence on the results. So if you have experience in simulating natural hazard phenomena and in using models to describe, for example, the propagation or runout behavior of debris flows, you are aware of the implications of setting a certain numerical parameter beforehand, before simulating, and then comparing the simulation results, for example, with a occurred event. So you have to adjust these parameters because the model normally is not capable of adjusting the parameters throughout, or let's say in due course of the simulation. So you need to define a number of scenarios to take into account this natural variability. A second source of variability, of uncertainty, is related, for example, to the so-called system loading assumptions. By system loading assumptions, I'm referring to, for example, the duration intensity of rainfall. So there, obviously, you have certain scenarios to take into account related to a certain recurrence intervals, for example, but also uncertainties related to sediment transport rates, depending on the precision and accuracy of the description of the solid layer. For example, a certain discharge may entrain different solid transport rates depending on the armoring of the mountain stream layer, depending on other initial and boundary conditions. Uncertainties emerging from wood transport, for example, it has been recognized also by flood risk managers that wood transport is a relevant problem at bridges in particular, but also at other rather constrained flow sections. So also the uncertainties related to the assessment of wood transport are always quite large and need to be addressed by the definition of dedicated scenarios. Third, there are uncertainties in the response system mechanisms. By response system, I'm referring to what is happening in the affected areas, for example, at the alluvial fan, where the settlements normally are located in alpine regions. In this case, the foreseen flow pattern might change due to obstructions at bridge cross sections that divert the flow pattern. And so you have to take into account by defining scenarios exactly what is happening at these critical configurations that might influence the flow propagation quite significantly. Also, the influence of small-scale topological features like walls that are somehow constraining the flow. If these topographical features are not well represented in your digital elevation model, for example, you risk to somehow overestimate the extent of the flood, or to underestimate in certain areas the effects of the flood. Fourth, we can talk about uncertainties concerning the protection system functionality. Imagine that this is particularly true in the alpine regions. Protection systems have been built through the entire last century and even before in many European countries of the alpine region. And depending on the state of maintenance, on the state of functionality of such protection systems, the hazard process obviously is affected, that is influenced by the performance of the protection system, and the reliability of the protection system might influence as well the hazard process. So if, for example, a staircase-like protection system built of several check dams along the stream is going to fail, obviously the availability of sediment to be transported downstream by the flow is changing abruptly, and therefore these scenarios have to take into account exactly the possible behavior of the protection system. If you want another example, if you're talking about the behavior of certain sediment retaining structures or sediment filtering structures, depending on the functionality of the retaining mechanisms and filtering mechanisms, obviously the process is affected in a significant way. So, and this is not always cannot always described with accuracy by numerical models at this scale. So, particular scenarios might be used to identify the range of behavior of, for example, filtering check dams, open check dams, retention basins, and so on. Another particular example is the example of flood inundation. There are obviously dikes built to confine the flow, let's say, to the active river channel, might also fail, and if such failures occur, inundation patterns might diverge from the, let's say, inundation patterns that would result from a configuration without dike failures. Uncertainties can also be related to morphological changes that induce hazard processes or amplify their disposition. Just to make some examples, erosion phenomena in alluvial channels or alluvial fans, flow path changes in steep mountain rivers, for example. This is very important. These uncertainties can be addressed by using a geomorphological approach, and this would be what we are calling also geomorphological risk. That means that there is a variability of responses in terms of geomorphological dynamics that is not well